faster than the fabric of space-time can. Keep up with it, and it'll just rip. I'm terrified by this currently our night. Sky is changing rapidly, and in just a matter of decades, if not years, it might become completely unrecognizable. Astronomers worldwide are sounding the alarm. Experts like deGrasse Tyson have recently confirmed the imminent explosion of Polaris and the tale behind. It is quite frightening. Polaris, known as the North Star, has long been a constant in our night skies, serving as a crucial reference point for stargazers, navigators, and astronomers. However, this might soon change, altering our night sky and astronomical measurements indefinitely. Let's delve into the significance of this threat and its implications for all of us. Join us as we uncover the story of Polaris as it approaches its end. For centuries, Polaris has guided mariners and astronomers alike, holding a revered position as a guiding light. Its unwavering presence in the night sky has been essential for navigation, but this stability may soon be disrupted. In September 2023, a research paper presented by the esteemed Royal Astronomical Society cast doubt on the fate of the celestial luminary Polaris. It is on the brink of exploding, potentially vanishing from the night sky forever. Before we explore the consequences of this revelation, let's understand more about Polaris, also known as the North Star or Pole Star. Polaris is special due to its proximity to the celestial North Pole, situated almost directly above Earth's North Pole. It appears almost stationary in the northern sky, found in the constellation Ursa Minor or the Little Dipper. Polaris shines as a moderately bright yellow-white super giant star, much larger and brighter than our Sun. It's not a solitary star, but part of a complex triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris B orbits around them. The interactions among these stars create gravitational forces, shaping their orbits and influencing their behavior. Any disruptions in these interactions can lead to irregular variations in the star's brightness or pulsation patterns. However, the exact mechanisms behind these interactions remain unclear. Polaris is located approximately 323 light-years away from Earth, meaning the light we see from it today started its journey over 3 centuries ago. Thus, if Polaris were to explode now, we wouldn't observe it until over 3 centuries later. It's even possible that Polaris has already exploded, and we're yet to witness the light from that event. Throughout history, the North Star has held immense cultural, navigational, and symbolic significance. Its stability and fixed position made it an invaluable aid for ancient navigators, guiding them across seas and lands. Symbolically, Polaris represented constancy and guidance, remaining steadfast amidst the ever-changing night sky. For astronomers, Polaris served as a crucial reference point, aiding in the study of celestial motions and variable stars. As a side variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a pivotal role in determining cosmic distances and calibrating instruments. These pulsations follow a predictable pattern which has been the norm for the star, making it easy for us to anticipate its behavior. However, recently Polaris has strayed from this expected behavior. This irregularity in its pulsation cycle has puzzled astronomers, leading to a closer examination of the celestial anomaly. Instead of its usual predictable pattern, Polaris has begun displaying erratic cycles of dimming and brightening. Scientists are now raising concerns that the star may be approaching the end of its life. This aligns with behaviors typically observed in stars nearing their end. A gradual elongation of Polaris's pulsation period, which was once stable, can be attributed to interactions within its star system. We've observed an annual increase in the pulsation duration of 4.5 seconds, which might seem insignificant, but it holds significant implications. Some astronomers suggest that gravitational interactions between the Polaris stars could be causing these fluctuations in its atmospheric conditions, directly affecting its pulsation patterns. However, others are more alarmed, believing that the star is on the brink of exploding. The similarities between Polaris's behavior and that of Betelgeuse, another notable star in the Orion constellation, are striking. Both stars have shown perplexing irregularities in their luminosity, raising concerns about potential explosions. Stars in their twilight stage often exhibit such irregularities before reaching the culmination of their life cycles. NASA has expressed heightened concern about Betelgeuse, but similar attention hasn't been officially directed toward Polaris yet. As a Sage star nears the end of its life cycle, it progresses through various phases, including the main sequence phase, the red giant phase, and ultimately the supernova explosion. Based on Polaris's irregular pulsations, scientists predict it has entered the stages of helium depletion (TYP) of stars. Nearing their end, these irregularities in Polaris's behavior align with patterns indicative of seed stars in their twilight phases, but definitive indications of its nearing supernova remain inconclusive. Astronomers are diligently analyzing these irregularities to understand Polaris's fate. If Polaris were to go supernova, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance might drastically change, temporarily altering our perception of familiar constellations like the Big Dipper or Urs Minor, of which Polaris is a part. Rest assured, the Earth would likely be perfectly safe, even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually spectacular as that of Betelgeuse, it could still be visible to the naked eye for an extended period and outshine nearby stars. Astronomers and observers' Tories would undoubtedly take notice, sparking intrigue within the scientific community and among stargazers worldwide. However, the specific visibility and impact on Earth's atmosphere or surroundings would be less significant compared to a closer supernova event. But what about Polaris itself? What will be its fate after a potential supernova event? Let's clarify one thing. While giant stars typically end their lives with a supernova, this is unlikely to be the case with Polaris. When a massive star goes supernova, a massive explosion occurs within it, marking the final cataclysmic stage in its life. This process involves a complete collapse of the core, triggering an intense shock wave that causes the star to explode violently. However, Polaris is not massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transformation won't residential result in a supernova, but rather a serene conclusion as it evolves into a small, extremely dense stellar remnant. A white dwarf is a remnant of a low or medium mass star that has exhausted its nuclear fuel. It's incredibly dense, about as massive as the sun, but compressed to the size of Earth. When this happens, we will no longer be able to see its remnants from our planet, much like we observe the star today. Comparing the anticipated effects of Polaris's burst with historical supernova occurrences provides valuable insights into the evolution of stars and their ultimate fates. Comparing our expectations with well-documented supernova like SN 1987A and more recent events such as SN 2011 Fe or SN 2014J provides valuable data for understanding the potential aftermath of Polaris's burst, for example. SN 1354 resulted in the formation of the Crab Nebula, a nebula that continues to expand and emit radiation across multiple wavelengths, offering astronomers a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, provided insights into the processes of nucleosynthesis and the dynamics of supernova remnants, analyzing phenomena such as the formation of nebulae. The release of cosmic rays and variations in luminosity can offer insights into Polaris's unique characteristics. The formation of nebulae, like the Crab Nebula, results from the expulsion of material during the supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the cycle of stellar birth and death. Additionally, the release of cosmic rays, high-energy particles accelerated by supernova shock waves, has implications for astrophysical processes and cosmic radiation environments. To make a definitive comparison, scientists evaluate differences in mass composition and speed of ejected materials between Polaris's anticipated burst and other observed events. This involves studying the light curve spectra and remnants from these events and projecting similar characteristics for Polaris's anticipated burst, assessing whether Polaris's burst might lead to the formation of nebulae or distinct elemental distributions enhances our understanding of its potential outcomes. Another crucial area of investigation involves evaluating the pulsational variability of stars nearing their end stages, akin to Polaris again observed supernova precursors. This comparative analysis can help gauge similarities or deviations and provide insights into the burst mechanism. Pulsational variability in stars nearing the end of their lives may be indicative of internal instabilities or impending catastrophic events, offering clues to the evolutionary processes leading to supernova explosions. Despite meticulous observations and extensive analysis, astronomers find themselves puzzled by the irregularities observed in Polaris's behavior. Unraveling the unique conditions driving these irregularities holds the key to advancing our comprehension of stellar evolution. Understanding the mechanisms responsible for Polaris's irregular pulsations requires interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a crucial reference point in the night sky poses substantial concerns for astronomical endeavors. Ground-based telescopes and celestial measurements would require recalibration, impacting the accuracy of astronomical assessments. The absence of Polaris could also affect navigation systems and cultural practices reliant on celestial landmarks, underscoring the significance of this celestial event. The enigmatic behavior exhibited by Polaris underscores the necessity for deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its irregular pulsations and present concrete answers, recognizing the importance of advancing our understanding of celestial intricacies. Ultimately, the answer to Polaris's fate remains uncertain, and only time will reveal its true nature. Nonetheless, the pursuit of knowledge and understanding in the face of cosmic uncertainty is a testament to the enduring curiosity of humanity in unraveling the mysteries of the universe. The implications of Polaris's potential transformation extend beyond mere astronomical interest. They touch on the very fabric of how humanity understands its place in the cosmos. Throughout history, celestial bodies have served as markers of time and navigation, guiding explorers across uncharted waters and lands. The loss of Polaris would not only disrupt traditional navigation methods, but could also have far-reaching effects on cultural mythology and symbolism tied to the North Star in various cultures. Polaris has been integral to folklore and spirituality. For example, Native American tribes often viewed Polaris as a guiding light in their stories, symbolizing hope and endurance. Similarly, ancient Egyptians used the North Star in their architectural designs, aligning pyramids with its position in the sky. The disappearance of such a pivotal star could alter cultural narratives and the collective human experience related to navigation and orientation. Additionally, the scientific community stands to face significant challenges if Polaris were to vanish. Astronomic measurements and observations heavily rely on established reference points. Polaris's role as a constant has facilitated the calibration of instruments and models used to study distant galaxy star formations and even the expansion of the universe. The sudden absence of Polaris would necessitate recalibrating many of these systems, potentially leading to discrepancies in measurements and understandings of cosmic phenomena. As astronomers shift their focus to monitoring Polaris more closely, new observational technologies are being developed. Advancements in spectroscopy and photometry allow scientists to analyze light emitted by stars in unprecedented detail. These tools help in detecting minute changes in brightness, which are crucial for understanding the mechanisms driving stellar behavior. As researchers gather more data, they hope to refine their models of stellar evolution, particularly concerning stars in the later stages of their life cycles. The study of other similar stars, such as Cepheid and red giants, offers insights that may prove invaluable. For instance, astronomers are observing variables like the period-luminosity relationship, which helps in measuring distances across the universe. By comparing these stars' behaviors to those of Polaris, scientists hope to gain a clearer understanding of stellar dynamics and evolution, enriching their comprehension of our galaxy architecture. Moreover, as the search for exoplanets intensifies, the study of Polaris and its companions becomes more significant. Understanding the characteristics of stars in triple systems can provide crucial insights into the formation and habitability of planets orbiting them. Astronomers are keenly interested in how such stars influence their surroundings, potentially affecting the conditions under which planets form and evolve. If Polaris does experience a significant event such as a pulsation leading to its transformation, it may also serve as a natural laboratory for studying the life cycles of stars. Such occurrences would not only provide a window into stellar depth, but could also illuminate aspects of nucleosynthesis, the process by which elements are formed in stars. The remnants of Polaris could contribute to the interstellar medium, enriching it with heavy elements essential for the formation of new stars and planets.